September 21st, 2003. $1 billion of hardware is screaming through the upper atmosphere of Jupiter. This is the Galileo spacecraft. For 14 years, it has been our eyes and ears in the darkness of the outer solar system. It has rewritten the textbooks on gas giants. It is a hero of exploration, and we are murdering it. We didn't lose the signal. We didn't have a malfunction. We commanded it to die. We fired its thrusters to ensure it would burn up at 106,000 miles per hour, vaporizing every ounce of aluminum, silicon, and plutonium it carried. Why? Because of a single, terrifying possibility. Galileo was running out of fuel. If we lost control, there was a mathematical chance, small but non-zero, that it could crash into a moon called Europa. And if even a single microbe from Earth was hiding inside its chassis, sleeping for 14 years in the cold vacuum, that crash wouldn't just be an accident. It would be an invasion. We destroyed the messenger to save the message. Now, decades later, we are going back. The Europa Clipper is en route, a $5 billion flagship designed to stare directly into the abyss of that alien ocean. But there is a dark secret built into its flight plan. We are not just planning a mission of discovery. We are planning another execution. To find life, we have to be willing to kill our own creations. But this time, the target isn't Jupiter, and the stakes are no longer theoretical. I want you to look at Europa not as a moon, but as a petri dish. For decades, we have been obsessed with the physics of space travel. Delta V, specific impulse, orbital insertion. But the real barrier to finding life isn't propulsion. It's biology. Specifically, our biology. We are dirty. As a species, we are covered in a microscopic fog of bacteria, fungi, and spores. We build our spacecraft in clean rooms. We scrub them with alcohol. We bake them in ovens. But we can never get them perfectly sterile. Life is tenacious. We have found bacteria thriving in the cooling water of nuclear reactors. We have found spores on the outside of the International Space Station. If we send a probe to Europa, and that probe crashes, and a single Bacillus subtilis spore survives the impact, what happens? Europa has liquid water. It has heat. It has organic chemistry. It is the perfect incubator. That single Earth spore could replicate. In 1,000 years, it could colonize the subsurface ocean. If we then send a submarine to search for alien life, all we will find is the great-grandchildren of the bacteria we brought with us. Or worse, we could introduce a pathogen that outcompetes whatever fragile native life has been evolving there for 4 billion years. We wouldn't just be discovering a second Genesis. We would be extinguishing it. This is the nightmare scenario of forward contamination. Before we analyze the engineering solution to this problem, I want to ask you a favor. If you appreciate space content that respects your intelligence and avoids the hype, please subscribe to support CosmoQuest 888. It helps us keep the signal clear. The fear of contamination drives everything. It is the reason why the Europa Clipper, the most advanced astrobiology scout ever built, is strictly forbidden from ever touching the world it was built to study. But prohibiting a crash is easier said than done. Gravity is a relentless opponent. To understand why, we have to look at the architecture of the mission itself. Most people assume that to study a moon, you orbit that moon. You arrive at Jupiter, you brake, and you slip into a nice circular orbit around Europa. You stare at the surface 24/7. Clipper won't do that. It can't do that. Radiation is the first reason. Europa sits deep inside Jupiter's magnetic field, a donut-shaped kill zone of high-energy particles. If Clipper stayed in orbit around Europa, its electronics would be fried in months. It would be a suicide run before the science even started. So, the mission designers chose a highly elliptical orbit around Jupiter. The spacecraft will dive in, scream past Europa at high speed to grab data, and then retreat out into deep space to upload the data and let its sensors cool down. It will do this nearly 50 times. But the second reason for this looping orbit is planetary protection. If Clipper were orbiting Europa and its main engine failed, gravity wins. The orbit decays. The spacecraft crashes. The ice is breached. The timeline for contamination begins. By keeping the spacecraft in a wide orbit around Jupiter, we buy time. If the engine fails at the top of the arc, furthest from the planet, the spacecraft just becomes another dead rock orbiting the gas giant, millions of miles away from the biological danger zone. But safe is a relative term in orbital mechanics. The Jupiter system is crowded. It has 95 moons. Their gravity tugs and pulls. Over decades or centuries, a dead spacecraft's orbit will wobble. This is chaos, theory in action. We cannot predict exactly where a derelict ship will be in 50 years. It might hit Callisto. It might hit Ganymede. Or, inevitably, it might be pulled into the one place it must never go. We cannot leave a dead ship in the Jovian system. It is a ticking biological time bomb. So, we need a disposal plan, a way to remove the threat entirely. And the solution they found is both brilliant and heartbreaking. To understand the solution, we first have to understand why the obvious choice was impossible. When the Galileo spacecraft reached the end of its life, we sent it into Jupiter. It was a clean death. The atmospheric pressure crushed it, and the heat vaporized it. No biology could survive that. So, why can't we just do the same with Europa Clipper? It comes down to a fundamental law of orbital mechanics that is often misunderstood. It is incredibly difficult to fall into the Sun, and it is almost as difficult to fall into Jupiter. When a spacecraft is orbiting a planet, it has a tremendous amount of sideways speed, or angular momentum. To hit the planet, you can't just point the nose down and fire. You have to cancel out that sideways speed. You have to hit the brakes hard. For a spacecraft in a wide orbit like Clipper, dropping into Jupiter's atmosphere would require a change in velocity, a delta V of hundreds of meters per second. That requires fuel, a lot of fuel, and fuel is the most precious commodity in spaceflight. Every kilogram of hydrazine propellant we load into the tanks is a kilogram of scientific instruments we have to leave behind. Galileo could do it because it was a different beast. It carried a nuclear power source, RTGs, which are heavy and compact. Europa Clipper relies on solar power. To capture the dim sunlight at Jupiter, 5 times further from the Sun than Earth, it needs massive solar arrays. These wings span 100 feet. They make the spacecraft huge, fragile, and difficult to maneuver quickly. The engineers crunched the numbers early in the design phase. To carry enough fuel for a Jupiter impact would have meant removing the ice-penetrating radar or the high-resolution camera. It was a non-starter. We built this ship to do science, not just to die. So, the Viking funeral into the gas giant was ruled out. Then someone asked, what about just pushing it out of the system, ejecting it into deep space? Again, the math is cruel. To escape Jupiter's gravity, well, once you are deep inside, it requires even more energy than crashing into it. We are trapped. We are bound to the king of planets. This left us with only one option. We had to crash it into a moon. But which one? This is where NASA procedural requirement 8020.12d comes into play. This document is the Bible of planetary protection. It dictates the rules of engagement for alien worlds. For a mission to Europa, the requirement is stark. The probability of contaminating the European Ocean with a viable Earth organism must be less than. That is 1 in 10,000. This isn't just a guess. It is a calculated threshold derived from decades of biological modeling. It considers the hardiness of spores, the radiation environment, and the likelihood of the ice shell breaching. The engineers at JPL had to build a probabilistic risk assessment, a massive decision tree that models every possible way the mission could fail. What if the thrusters clog? What if a micrometeoroid shatters the main computer? What if the solar panels degrade faster than expected? The model showed that leaving the spacecraft drifting in orbit was too risky. Over 50 or 100 years, the complex gravity of the Jovian system would act like a chaotic pinball machine. Eventually, the odds of hitting Europa rose above that 1 in 10,000 limit. We needed a definitive end. We needed a target that would destroy the spacecraft and its biological cargo, but that wouldn't itself be contaminated by the wreckage. We needed a Type 3 target. In Planetary protection terms, a Type 3 body is a world of chemical evolution interest, but with no significant chance of liquid water interacting with the surface. This sounds simple until you look at the candidates. Io? It's covered in volcanoes. The radiation there is so intense it might fry the computer before we could execute the crash, leaving us with a derelict ship. Callisto? It's too far away. Getting there would take too much time and fuel. That left the giant. Ganymede. Ganymede presents a fascinating paradox. It is the largest moon in the solar system, bigger than the planet Mercury. Like Europa, it has an icy surface, and like Europa, we are almost certain it has a subsurface ocean of liquid water. So, why is it a crime to crash on Europa, but a valid strategy to crash on Ganymede? Are we just being hypocrites? The difference lies in the ice. Europa is geologically alive. Its surface is young, crisscrossed with cracks and ridges. We see evidence of cryovolcanism, water, erupting from below. The ice shell is relatively thin, perhaps only 10 to 20 kilometers in places. If we drop a dirty spacecraft on Europa, geological processes could cycle that debris down into the ocean on a timescale of mere millions of years. It's a direct elevator to the habitable zone. Ganymede is different. Its surface is ancient and cratered. The ice shell is estimated to be much thicker, perhaps 100 kilometers or more. Crucially, the geophysics of Ganymede suggests it is in a stagnant lid regime. The ice isn't churning. There is no subduction. If we crash on Ganymede, the debris stays on the surface. It is locked in a frozen tomb, separated from the deep ocean by 50 miles of solid, immovable ice. The Planetary Protection Officer signed off on the plan. The probability of an Earth organism surviving the crash on Ganymede and migrating through that thermal barrier to the ocean was calculated to be effectively zero. So, the destination was set. But hitting a specific spot on a distant moon with a spacecraft running on fumes after years of radiation damage is one of the hardest navigation challenges ever attempted. Fast forward to September 2034. The Europa Clipper has survived 4 years in the harshest radiation environment in the solar system. The solar panels are brown and degraded, their efficiency cut in half by the relentless bombardment of high-energy protons. The reaction wheels, which spin to keep the spacecraft steady, are showing signs of friction wear. The fuel tanks are nearly empty. The science is done. The data has been downloaded. The maps are complete. It is time to say goodbye. The mission control room at JPL will be quiet. There won't be the cheering you see during a landing. This is a funeral service. The navigation team will calculate the final trajectory correction maneuver. They aren't aiming for a safe orbit anymore. They are aiming for the ground. They will select a region on Ganymede carefully, likely an area we have already mapped in high resolution, so we can see before and after images if a future mission ever visits the crash site. They want to avoid any potential young craters or interesting geological anomalies. We want to hit boring ice. At this pivot point between exploration and destruction, I have a request. Real discovery requires the discipline to destroy what you love. Please like this video and subscribe to support CosmoQuest 888 if you believe that protecting these worlds is just as important as exploring them. The command is sent. It takes nearly 45 minutes for the radio signal to cross the abyss between Earth and Jupiter. The spacecraft receives the order. It slews its orientation, turning its main thrusters to face the direction of travel. This is a retrograde burn. It fires the engines. The blue flame of the hydrazine monopropellant flickers in the darkness. This burn removes orbital energy. The spacecraft slows down. And as it slows, gravity takes over. The lowest point of its orbit, the periapsis, drops. It drops below the altitude of the terrain. The die is cast. There is no turning back now. As Clipper falls toward Ganymede, it accelerates. Jupiter's gravity is still pulling at it, but Ganymede's gravity is now reaching out too. The velocity at impact will be staggering. We estimate it will hit the surface, traveling at roughly 6,000 miles per hour. That is nearly 3 kilometers per second. To put that in perspective, a rifle bullet travels at about 1 kilometer per second. The spacecraft is a bus-sized bullet moving 3 times faster than a gunshot. Kinetic energy is defined by the equation: the mass is large, the velocity is squared. This means the energy released upon impact is enormous. When Europa Clipper strikes the ice, it won't just crumple like a car in a crash test. It will undergo shock metamorphism. The structural aluminum will behave like a fluid. The plastic, the copper, the glass lenses, everything will be compressed and heated instantly. This heat is the final sterilization step. Remember those 300,000 bacterial spores hiding in the screws and washers? The ones we couldn't scrub off? The energy of the crash will flash heat the immediate impact zone to thousands of degrees. It creates a localized fireball of plasma and vaporized ice. Any biological material is broken down into its constituent atoms: carbon, hydrogen, oxygen. The DNA is denatured. The information it carried is erased. The biological threat is neutralized not by policy, but by physics. But this violent end serves another purpose. It provides closure. If we simply turned off the transmitter and let the spacecraft drift, we would always wonder, where is it? Did it crash yet? Did it hit Europa? By executing a controlled crash, we know exactly where the bodies are buried. We close the book on the mission with certainty. We ensure that 100 years from now, our descendants won't have to worry about cleaning up our mess. However, even the best plans have margins of error. And this is where the story gets complicated. What if the burn fails? What if the engine cuts out halfway through? We would be left with a spacecraft in a grazing orbit, skimming the surface of Ganymede but not hitting it. This would be the worst-case scenario. A wounded ship, out of control, tumbling through the Jovian system with no fuel left to correct its course. The Planetary Protection Team has nightmares about this. It is why the fuel margins are calculated so conservatively. We save the last drop not for science, but for death. And there is a deeper philosophical question here. We are so afraid of contaminating Europa that we are willing to bombard Ganymede. We treat Ganymede as a trash can because we believe its ice shell is impenetrable. But science is always evolving. Just a few years ago, we thought the moon was bone dry. Now we know there is water in the shadows. We thought Venus was geologically dead. Now we see evidence of active volcanoes. What if we are wrong about Ganymede? Recent data from the Juno mission has complicated the picture. When Juno flew past Ganymede in recent years, it sent back images of the surface with unprecedented clarity. We saw grooved terrain, vast swathes of the moon that look like a plowed field. These are tectonic scars. They are evidence that the ice shell of Ganymede has been stretched, pulled, and fractured by tidal forces from Jupiter. While we still believe the ice is too thick for direct communication with the ocean, the surface is not as static as a concrete wall. It is dynamic. If we crash a probe into a fresh fracture zone, could the heat of the impact create a temporary melt pool that trickles down? It is unlikely. But unlikely is a dangerous word in planetary protection. This highlights the uncomfortable hierarchy we have constructed. We have decided that Europa is the premium target, the one worth saving at all costs. Ganymede is the secondary target, the one we are willing to sacrifice. We are playing favorites with alien ecosystems we haven't even discovered yet. We are making a calculated bet that life is more likely on Europa, and therefore Europa deserves the shield, while Ganymede gets the bullet. It is a pragmatic decision, but it sits heavy on the conscience of many astrobiologists. So, why don't we just build a perfectly sterile spacecraft? Why not heat the whole thing to 500 degrees and kill every single spore? The answer is frustration. We physically can't. Modern spacecraft are not made of solid steel. They are made of carbon fiber composites, delicate glues, optical coatings, and plastic polymers. If you heat a modern computer chip to 200 degrees Celsius, you destroy it. If you autoclave a camera lens, you melt the adhesive that holds the glass in place. We are trapped by our own technology. We need sensitive instruments to detect life, but those same instruments cannot survive the sterilization process needed to protect life. We use vapor hydrogen peroxide to fog the clean rooms. We wipe surfaces, but there are hiding spots we can't reach. The potting compound, the black epoxy goo used to seal electronics, is a perfect bunker for microbes. If a spore falls into the liquid epoxy before it cures, it is trapped inside the solid block forever. It is safe from the vacuum, safe from the UV radiation, safe from the chemical wipes. But in a high-velocity crash, that epoxy shatters. The bunker is breached. The spore is released. This is why we can never claim a spacecraft is sterile. We can only claim it is clean. And there is a world of difference between the two. This reality forces us to look at the future of exploration with a critical eye. If we ever want to land on Europa, not just fly by, but actually touch the ice and drill down, we need a revolution in engineering. We need materials that can withstand total sterilization. We need electronics that can work after being baked at 500 degrees. Until we have that technology, every mission is a compromise. Every landing is a biological gamble. Consider the Viking landers in the 1970s. They were baked in a giant oven for days. They were arguably the cleanest machines ever sent to Mars. But even they weren't perfect. And today, with our complex rovers like Perseverance and Curiosity, we have actually taken a step backward in cleanliness because the rovers are too big and complex to be baked. We are sending dirtier machines to Mars now than we did 50 years ago. We get away with it because we land in dry, irradiated deserts where we think life can't exist. But Europa offers no such safety net. The ice is the door to the ocean. You knock on the door, you risk letting the contagion in. This brings us to the final phase of the Europa Clipper's journey. The end of mission plan is not just about disposal. It is a data point. When Clipper hits Ganymede, the impact flash might be visible to telescopes on Earth or in space. The spectral signature of that flash, the light breaking down into colors, will tell us exactly what the spacecraft was made of at the moment of death. It sounds morbid, but it is useful. It helps us model impact physics for future asteroid deflection missions. Even in death, the machine provides data, but for the scientists who spent 20 years building it, the moment will be silent. There is no video feed from the surface of Ganymede. The high-gain antenna will be pointed away from Earth during the maneuver. we will see the telemetry stop. The heartbeat of the carrier wave will flatline, and we will know that somewhere, 600 million kilometers away, a new crater has been formed. A crater containing titanium, silicon, and the ashes of human curiosity. In the end, the destruction of Europa Clipper is an act of humility. It is an admission that our technology has limits, and that our presence in the universe carries consequences. We are not just observers, we are participants. And sometimes, the most respectful way to participate is to leave no trace. When we look back at the history of space exploration, we see a pattern of increasing caution. The Soviets crashed the Luna 2 probe into the moon in 1959 without a second thought about bacteria. We crashed Ranger probes. We left bags of trash on the lunar surface during Apollo. But as we moved outward, to Mars, to Jupiter, to Saturn, we started to realize the magnitude of what we were touching. We realized that the solar system isn't just a collection of rocks. It is a collection of environments. The sacrifice of the Europa Clipper on the fields of Ganymede is the price we pay for that realization. It ensures that the pristine ice of Europa remains a mystery for just a little longer. It buys us time to develop better drills, better sensors, and better sterilization methods. It preserves the scientific integrity of the site for a generation that hasn't been born yet. There is a concept in wilderness ethics called leave no trace. You pack out what you pack in. You don't carve your name on the trees. In space, leave no trace is impossible. We leave footprints. We leave rovers. We leave craters. But we can choose where we leave them. We can choose to limit our impact. We can choose to protect the places that might, just might, harbor a second genesis of life. This mission will teach us more about Europa than any mission before it. We will map the cracks. We will taste the dust sputtered off the surface. We will measure the thickness of the ice. But the most important legacy of the Europa Clipper might not be the data it sends back. It might be the bacteria it takes with it to the grave. By destroying the ship, we keep the promise. We keep the ocean pure. We keep the question open. And in science, an open question is always better than a contaminated answer. As we conclude this deep dive into the planetary protection protocols of the 21st century, want to turn the final question over to you. This is a debate that divides the scientific community. Some argue that these strict rules are slowing down exploration, that we should just land, take the risk, and see what happens because the odds of Earth bacteria surviving are so low. Others argue we aren't strict enough, that we shouldn't send probes at all until we can guarantee 100% sterility. So, here's the question for the comments. Do you think NASA is being too cautious by destroying a $5 billion spacecraft to protect a hypothetical ecosystem? Or should we avoid going near Europa entirely until our technology improves? I read every comment, and I want to know where you draw the line. If you enjoyed this analysis and want to support high-quality, calm space documentaries, please verify you are subscribed to CosmoQuest 888. It is the best way to help us continue this work. The universe is vast, and we are just learning how to walk through it without breaking things. The Europa Clipper is our latest step. It is a step taken with excitement, but also with care. It is a mission that ends in fire, so that the ice remains frozen. Thank you for watching. We will see you in the next orbit.